In Chapter 3, Section 2, we're going to continue with the structure of the atom. Our objectives today are to summarize the observed properties of the cathode rays that led to the discovery of the electron, summarize the experiment carried out by Rutherford and his co-workers that led to the discovery of the nucleus, list the properties of protons, neutrons, and electrons, and define an atom. We've already talked about an atom. An atom is the smallest particle of an element that retains the chemical properties of that element. We saw that in Chapter 1 when most of you scored very well on the first test. We've also talked about in Chapter 1, you've learned in elementary and middle school that the nucleus is a very small region located at the center of an atom. The nucleus is made of at least one positively charged particle called a proton, and usually one or more neutral particles called neutrons. Surrounding the nucleus is a region occupied by negatively charged particles called electrons. So today we know about these three main subatomic particles: protons, neutrons, and electrons. The chart, you don't have to memorize it, but know in general that an electron, we'll see it has a lowercase e for a symbol, and electrons have a -1 charge. Protons, you may see a symbol of P+, because protons are +1. A neutron, you may see a lowercase m. They have no charge to it. And from careful measurements, you don't have to memorize the actual mass numbers, but just know protons and neutrons are nearly equal in mass, but an electron, it's about 10,000 times lighter. So electrons essentially have no mass in an atom because they're so light compared to the other two. For the discovery of an electron, yes, you do have to know a few dead guys. It's good to know history as we develop things sometimes. We really didn't discover electrons, well, not we personally, but electrons weren't discovered until around 1900 because electricity wasn't harnessed until that time. So some of the major chemistry and physics ideas and laws weren't discovered until recently. They're not thousands of years old. Experiments in the late 1800s show that cathode rays were composed of negatively charged particles. These particles were called electrons because if you translate the word electron from Greek, it means negative. Kind of looks like a fluorescent light bulb. What they did, they connected a voltage source to this tube that was called a cathode ray tube. It was also hooked up to a vacuum pump to evacuate all the air around it so there wouldn't be any interference in the measurement. So what happened, electricity was passed through the tube and measurements were taken. So the dead guy who really is attributed to this, his name was John Joseph Thomson. Most of the time he's just called J.J. Thomson. So his cathode ray tube measured charge to mass ratio of an electron. So what he did, he put a negative magnet next to the cathode ray tube, and he was able to measure that the electricity going through it was deflected by a negative, because a negative will repel a negative. If he used a positive, it would attract the electricity, because positives, the opposites attract. A second was an American physicist named Robert Millikan. He did an oil drop experiment and he measured the charge of an electron. And when he measured the charge of an electron, he was also able to measure the mass of an electron. And that's how we know that the electrons are so much lighter than some of the other subatomic particles. A little bit later, after Millikan's experiment, there's a famous gold foil experiment. It was performed in Europe by a scientist named Ernst Rutherford. So what he did, he took energy and shot it through a gold foil. You don't have to copy down this whole diagram, but the point of it, if we could have magnified it, just look at the different atoms. If there was no nucleus, it was expected, like these red lines, they would just go through. If just the positives and negatives were just scattered, in an atom. But what he found, when the energy went through, it was deflected. So because it was deflected, Rutherford was the main guy, and he had a couple associates. But because it was diffracted, that he was able to come with the results that there's a dense, packed bundle of matter, which is called a nucleus. So with his measure results, there's positive particles in a nucleus. And when he figured this out, he said, okay, we have something in the center, we know electrons exist around it, so kind of like our planets in the solar system, the explanation of an atom is called the planetary model after Rutherford, where the electrons orbit around the nucleus. Kind of like the planets orbit around the sun. So what we know today, except for the nucleus of the simplest type of hydrogen atoms, all atomic nuclei are made of protons and neutrons. A proton has a positive charge equal in magnitude to the negative charge of an electron. Protons are positive, electrons are negative. Atoms are electrically neutral because they contain equal numbers of protons and electrons when they're stable. A neutron has to exist because there had to be something else to account for the atomic mass. Electrons are so light that there had to be a third particle. So we do have neutrons in the nucleus, and neutrons are electrically neutral. The nuclei of atoms of different elements differ in the number of protons and therefore in the amount of positive charge they possess. So in plain old English, the number of protons determines that atom's identity. So if it has 1 proton, it has to be hydrogen. 2 protons has to be helium. That's how they've defined elements on the periodic table. So the number of protons is the same as the atomic number. That's the identity of an element. And lastly today, to finish out section 2, some of the forces that exist in the nucleus after they've been discovered. When 2 protons are extremely close to each other, there's a strong attraction between them, even though they're positives. So with careful measurements, they found that a similar attraction exists when neutrons are very close to each other, or when protons and neutrons are very close together. So these short-range proton-neutron, proton-proton, and neutron-neutron forces that hold the nuclear particles together are referred to as nuclear forces. We only are going to study the 3 subatomic particles in chemistry. We're not going to worry about quarks, baryons, mesons, leptons, some of the other things that are still theorized. If you take physics, maybe you might explore them in high school and college. So that's good for section 2. There's no math in sections 1 or 2, but that doesn't mean they're not as important as section 3. So review, refresh, see if you have any questions, but make sure that you study and prepare for chapter 3.